Alright guys, let's try this again. So consider the geometric series a sub 0 plus a sub 0 r and so on. We know that this series converges to a sub 0, that's first term, over 1 minus the common ratio, as long as r is less than 1, right? So it's dependent upon that common ratio, and as long as that common ratio is a fraction, everything works out, everything is okay. Well, what if we take this series here and we replace r with a variable? So let's replace r with x, because this series a sub 0 plus a sub 0 x plus a sub 0 x squared and so on is going to end up looking like the function a sub 0 over 1 minus x. That's if x is less than 1, right? So as long as x is within the range in this absolute value, as long as x is in between 1 and negative 1, we can say that the series f of x, I'm going to call it f of x, is going to be equal to this function g of x. So this series and this function are equivalent, but only in this interval, right? What we're going to call an interval of convergence, right? That is, the series and that series function f of x and g of x here are going to be the same, provided, one, you go out an infinite number of terms, and two, as long as g of x is this function here, okay? So let's simplify this. Let's get rid of a sub 0, and let's do as an example, f of x is equal to 1 plus x squared plus x cubed plus so on and so forth. And let's let g of x be equal to 1 over 1 minus x. And let's go ahead and let's try and graph these two things and see how it goes. So when I pull up the graph, this is the graph of f of x. This green graph right here is the function 1 over x. I'm sorry, I called that g of x in the other one. And then the series, what I had called f of x, is going to be this sum. Now, if I just go ahead and graph this for, say, the first two terms, right? 1 plus x, we get that line, which looks a lot like a linear approximation, right? It looks like a linear approximation of that function. Please note that function has a vertical asymptote at 1, right? Well, what happens if I add another term, right? So this is going to be the sum of 1 plus x. Well, if I make it 1 plus x squared, we have a quadratic approximation. The blue line is now quadratic. The g of x here, this sum, is quadratic. And if I start adding on more terms, we get a cubic approximation, 4th degree, 5th degree, 6th degree, so on. And what you'll notice here is as we zoom in, around 0, you're identical between the function 1 over 1 minus x and the series. And it looks like we're really close on both sides. And if I keep adding on terms, it gets closer and closer and closer and closer and closer between negative 1 and positive 1. Notice how they're nowhere near each other when you get out of that range from negative 1 to 1. But as long as we keep adding on terms, negative 1 to 1 will be pretty darn close, okay? This is a basic kind of power series where these things are the same, okay? So I'm going to post this worksheet up. I'm going to still go through some stuff. There's some series practice problems I want you guys to try. But there we go. We have a power series. F of x is equal to 1 over 1 minus x for this series as long as we're in this radius of convergence. So now let's mess around with this a little bit. All right. So, for example, that series was nice and it was centered at 0. Right? At 0, we were identical, and then in between positive and negative 1, that was your interval of convergence. Sometimes we say it has a radius of convergence of 1, in that from your center you're going to the right one and to the left one, and that's your radius, right? So this function is actually equal to 1 over 3 minus x, right? And if I want to write out some terms for this particular series, it would be 1 plus x minus 2 plus x minus 2 squared plus x minus 3 squared, and so on, right? Instead of 1 plus x squared and so on, we have this x minus 2, all right? This series, or sum, I can rewrite it as the sum n equals 0 to infinity of x minus 2 squared. All right? If we want to find out the interval and the radius of convergence, this is the general term right here that I wrote over on the left. The general term is x minus 2 squared, or I'm sorry, x minus 2 to the n squared. Let me correct that up here as well. It's got to be x minus 2 to the n, where n equals 0 to infinity, and anytime we're looking for the interval of convergence or the radius of convergence, we're going to use the ratio test. Which the ratio test, of course, if you remember, we take the limit as n goes to infinity of a sub n plus 1 over a sub n, and we want this to be less than 1. So we've got the limit as n goes to infinity, absolute value of x minus 2 to the n plus 1 all over x minus 2 to the n, which of course has to be less than 1. This is going to simplify to just absolute value of x minus 2 has to be less than 1. This one still ends up being our radius of convergence, 1 unit, but we're going 1 unit to the right and left of 2. So we would say that our interval of convergence is going to be 2 plus 1 and 2 minus 1, so that's going to be 1 to 3. And if I go ahead and go back to the graphing that we just did, let me pull this back up, and let's say I put in here x minus 2, right? Notice how that just shifted the asymptote over to 3, and now I need to shift my series over there as well. And so my series gets shifted by this x minus 2, 2 units to the right, and boom, there we go. Right? It's almost like the same function, just shifted to the right 2 units. Okay? Now this allows us to keep playing with our series and functions in various ways. So let's say, for example, I had this function, and I wanted to go ahead and find the general term and some series terms and so on and so forth. Well, this to me looks like 1 over 1 minus what? Well, negative x. So that's my common ratio. The series is going to go from n equals 0 to infinity, but instead of just x to the n power, this is going to be negative x to the n power. And of course, you may already kind of realize what this is going to do. This is going to create an alternating power series of 1 minus x plus x squared minus x cubed, and so on. Right? And we can find the interval and the radius of convergence by applying the ratio test up here. We can do the limit as n goes to infinity, absolute value negative x to the n plus 1 all over negative x to the nth power. Of course, this is going to be equal to just negative x. And of course, because this is a ratio test, in order to converge, we have to be less than or equal to 1. So x has got to be in between positive 1 and negative 1. Our radius of convergence equals 1, and our interval of convergence is going to be negative 1 to 1 because our center is at 0. Okay? You can go ahead and graph that. Graph the function f of x and graph a couple terms. Maybe try and go out a few terms. You don't have to use the summation notation if you don't want to. Go ahead and graph it and take a look at how those two things compare. Okay? Try the next one. You can pause the video and try and write some of it out. I will take care of it in a minute. All right. So I hope you were able to figure out that this, of course, is 1 over 1 minus 3x. I'm sorry, negative 3x. Woo. Right? There's got to be a negative in there, right? And so that's our common ratio. Our first term, of course, comes from the numerator 1. So this is going to be 1 times negative 3x to the nth power. Right? So that's our series. Could write out some of the terms of this. It's going to be 1, then minus 3x, then plus 9x squared, then minus 27x cubed, and then plus 81x to the 4th, and so on. Next one's going to be minus, all right, as it goes along. Okay? So let's apply the ratio test to the general term here and do limit as n goes to infinity of the n plus 1 term. So that's negative 3x to the n plus 1 all over negative 3x to the n. We can reduce that as n goes to infinity down to just negative 3x. This, of course, has to be less than 1 in order to converge by the ratio test. The absolute value is going to get rid of this negative right here. And then if we want, we can divide the 3 over, and we see the absolute value of x has to be less than 1/3. And so our radius, this time, of convergence is only 1/3. Our center is still at 0, so our interval is going to be 0 plus 1/3 and 0 minus 1/3, or negative 1/3 to positive 1/3. You can go ahead and plug it into a calculator again, write out a bunch of terms and so on, and see how you can do. All right, see how well it looks. You'll see it's only converged in that little interval of 1/3. All right, so I'd like you to continue working on this particular packet. Try and do some of the problems on the next page. Remember, our first term here for like the next problem, this is going to be our first term is x, and our common ratio is down here. Okay, and we can manipulate and get into all sorts of different problems here. I think this would show me that the sum n equals 0 to infinity is really x times 2x to the n. That can be kind of messed around with to make this sum look a little bit better, in that we can do 2 to the n times x to the n plus 1. All right, and kind of work it from there, write out a couple terms and so on, okay? So try this in the next problem for tonight. See if you can get up to see if you can try the problems on this page right here, and maybe the next page as well, okay? And then I'll start going over some more in my next video. All right, thank you guys for watching and listening. Pay attention for more stuff in the future. Thanks.